Hi everyone, this is the second video in a series of quantum chemistry classes. In this video, we shall learn about operators. See, in mathematics, it is very easier to perform any operation such as addition, division, multiplications, and even subtraction, like these things. Here we said 3 plus 3 directly will give the value of 6. 4 divided by 2, it will be 2. 2 into 5, we get the 10. 3 into 3, we're getting 9. So like this, performance of any operation is very much easier. But if you come to the case of quantum mechanics, it is not that much easier to perform any operation. If you want to perform an operation towards any function in quantum mechanics, there is a requirement of operators. And an operator means, in actual sense, an operator alone doesn't have any physical meaning. But when it operates on a function, it will produce one more function. This is the actual definition for operator itself. That means an operator is one whose work on a function will produce another function. So let us consider one simple example. Let you consider d by dx as an operator. When you perform this on a function, say for example 4x square, so on which we are performing an operator d by dx. So when you perform d by dx on 4x square, we are going to get 8x. So again, 8x is a function. So here d by dx will be considered as an operator. But when you perform the same operator d by dx on a function such as 4x, you're going to get 4, which is not a function, which is a constant. So here d by dx cannot be considered as an operator. So an operator in quantum mechanics, I am telling in case of quantum mechanics, an operator is one when it acts on a function, it's supposed to produce one more function. Okay, and that is the actual definition for operator. Shall generalize with respect to quantum mechanics. In quantum mechanics, if you say A as an operator, in order to represent that as an operator, we will place a cap on it. So any parameter which is having cap on it will be considered as an operator in the field of quantum mechanics. So if you consider a cap, if a cap is denoting an operator which can perform a function, which can perform an operation on a function, say f of x. Okay, so when an operator a cap is acting on a function f of x, that will produce one more function, say g of x. So this is the actual meaning of what the operator. So let us do some simple illustration. Let the operator a cap be what d by dx, and let f of x will be what we can say 2 or ax square. So a cap will be d by dx and f of x will be 2ax square. So shall perform the operation of d by dx on f of x, that is 2ax square, and that gives 4ax, which is nothing but g of x. And here what we did, here we perform the operation of differentiation. And let me consider one more exemplification or one more illustration. Let a cap be a term a, and the function f of x will be x square plus c. And if the operator a cap is acting on a function f of x, that means a of x square plus c. So we will be getting a x square plus ac, which is g of x, once again a function. And here in this case we actually performed the operation of differentiation, and here what we did, here we did multiplication, which is one of the operation. So let me say once again, an operator alone doesn't have any physical meaning, but when it comes into picture, that means when it deployed to operate on a function, it gains the meaning and it will produce once again a function. And in the field of quantum mechanics, we are having more number of operators, and in this session we shall learn about some of the important operators, such as first one, position operator, which is simply indicated with the notation x cap. Number two, momentum operator, which is indicated as p cap. Thirdly, kinetic energy operator, which is indicated with the notation t cap. And most importantly, Laplacian operator, which is indicated with the symbol del square. And number 5, Hamiltonian operator, which is indicated with the symbol h cap. And at the last, we shall say a bit about linear operator. So these are the operators we shall learn in this video. Firstly, let me consider the position operator, that is x cap. So this position operator will actually, what implies is, it simply is the multiplication by x. So that let me illustrate by considering one simple example. Say if x cap is square root of h cross by 2 pi omega. This is the value of x cap. And if you have an operator, say for example, if x cap is operating with xi, we know the meaning of xi, that is wave function. So x cap into psi. So here we said multiplication by x. So this implies that x cap is getting multiplying with xi. So we have the value of x cap, that is h cross over 2 pi omega multiplying with xi. This is the actual way of the term or the operator position. Number 2, it is momentum. We have the symbol for momentum, that is p cap. And let me consider momentum in one particular Cartesian coordinate, that is x. And now let me consider we have the meaning of momentum, that is mass into velocity. Momentum is actually the product of mass into velocity, right? So in quantum mechanics, the momentum operator actually means for minus I h cross into dou by dou x along x-axis. So we know the meaning of I is called as iota, which is nothing but square root of minus 1. So let me say, let me do some simple illustration to account for the momentum operator. Let xi is equals to a sine 2 pi x by lambda. So we already come across with this in our last video. This is called as sinusoidal wave equation. Sinusoidal wave equation. So if you go with an operator such as px cap into psi, this is the operation we are supposed to perform. So we have the value of px cap, that is minus I h cross into dou by dou x, and we have the value of xi, that is a sine 2 pi x by lambda. So this is the value of xi. So here we are performing the operation of differentiation on this particular function. So minus I h cross dou by dou x of a sine 2 pi x by lambda will be a cos 2 pi x by lambda over 2 pi by lambda. So that is the complete result we obtain, the function we got when the momentum operator is performed on a function xi. And that's about position and momentum operators. So thirdly, we shall go with kinetic energy. and we have the symbol for kinetic energy, that is T cap. Right. So kinetic energy. So simply we have the equation for kinetic energy, that is Ke is equals to half mv square. And just now in the last minute I said mass into velocity is simply nothing but momentum, that is P. Right. So in order, here we have one m term and one v term, but we two v terms, but we have mass into velocity is momentum. So let me manipulate this equation, half m v square, let multiply and divide it by m. So nothing will get changed. Once again, if m and m will get cancelled, the same expression will get. So half m square v square whole divided by m. And this m square v square can be replaced with the term 1 by 2 m. M square v square can be written as p square, that is p cap square, since the kinetic energy T cap is expressing in terms of, if we take in the kinetic energy operator along x-axis, 1 by 2m into px square. And we have the value for px cap, that is minus I h cross into dou by dou x. Right. So that is the value of px cap. And now, so here we have px cap square. So 1 by 2m into minus I h cross into dou by dou x whole square. So here we have the minus. So here we have the square. So minus into minus will be plus. And I will terms I square. So I is equals to square root of minus 1. So I square will be getting minus 1. Therefore, the term will get changed, minus h cross square by 2m into dou square by dou x square. That is the value of kinetic energy along x-axis. So when kinetic energy is measured in x-axis, we can get in remaining two Cartesian coordinates also, so as to get the total kinetic energy. That is T cap. So total kinetic energy T cap will be kinetic energy along x, kinetic energy along y, kinetic energy along z. So here we have the value for Tx cap, that is minus h cross square by 2m into dou square by dou x square plus Ty minus h cross square by 2m into dou square by dou y square plus minus h cross square by 2m into dou square by dou z square. And here we have minus h cross square by 2m common, dou square by dou x square plus dou square by dou y square plus dou square by dou z square. That is the complete of the total kinetic energy operator. So just remember this particular value what we got for total kinetic energy. And now we shall go to the next operator, the most important one, that is Laplacian operator. So which is indicated with the symbol del square. So if you go with thing in mathematics, for a three-dimensional coordinate, the differential operator, that is I dou by dou x plus I into dou by dou y plus I into dou by dou z, which is acting on a function f. So this will be simply given equals to del. Right. So when you have taken square of this del square, that will give us dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This del square is actually called as Laplacian operator. And where we can get this Laplacian operator? So that we shall observe in Schrödinger wave equation, what we have written for 3 dimensions in our last video, according to which dou square by dou x square plus dou square by dou y square plus dou square by dou z square of xi plus 2m by h cross square into e minus v of xi is equals to 0. So this is the 3-dimensional Schrödinger wave equation we have derived in our last video. And here you can observe dou square by dou x square plus dou square by dou y square plus dou square by dou z square, which can be written as del square. So the Schrödinger equation will get reduced to del square psi plus 2m by h square into e minus v of xi is equals to 0. So that here you can observe this Laplacian operator del square accounts for the x, y and z coordinates about its wave function. So that we can say this Laplacian operator mainly gives information about position of the system. That is the significance of Laplacian operator. Now the much more important one, that is Hamiltonian operator, which is symbolized as h cap. This Hamiltonian operator mainly accounts for total energy of the system. It accounts for total energy of the system. And we know that total energy is simply nothing but sum of kinetic energy and potential energy, which can be taken as V. And we have the expression for kinetic energy in terms of operator. We have given that kinetic energy is minus h cross square by 2m into dou square by dou x square plus dou square by dou z dou y square plus dou square by dou z square, right, plus v. So this is the sum of kinetic energy and potential energy. But just now we saw dou square by dou x square plus dou square by dou z square plus dou square by dou y square plus dou square by dou z square is nothing but del square. So we can modify this minus h cross square by 2m into del square plus v. That actually gives the value of Hamiltonian, that is nothing but Hamiltonian operator. And where we can observe this Hamiltonian operator? Again, we shall consider the same Schrödinger wave equation that we have derived in the last video, right? So according to which dou square by dou x square plus dou square by dou y square plus dou square by dou z square of xi plus 2m by h cross square into e minus v of xi is equals to 0. Right, this is the 3-dimensional Schrödinger wave equation, and we already observed this whole term can be replaced with del square xi plus 2m by h cross square into e minus v of xi is equals to 0. And let us do some simple manipulations. Del square xi is equals to, let us shift this to the right hand side, it will become minus 2m by h cross square into e minus v of xi, e minus v of xi. Now we shall do the cross multiplication. H cross square will come to the left hand side by 2m into del square xi. That's equals to e minus v of xi. So we shall do the multiplication. Minus h cross square by 2m del square psi. Here it will be E psi minus V psi. The V psi can be taken to the left hand side. That's equals to E psi. And now here we have the psi common. So minus h cross square by 2m del square plus V of psi is equals to E psi. And in the last concept we said minus h cross square by 2m into del square plus V is nothing but Hamiltonian. That is h cap into psi is equals to E psi. So here we have psi. If you cancel out these two, h cap will be equals to E. That's what I said in the very beginning. The h cap will give information about total energy of the system. Right. And this is the simplified mathematical expression for Schrödinger wave equation. And at last, we shall say about linear operator. It's a very simple one, the linear operator. So if you have an operator with you, and if you want to call that operator as a linear operator, it should satisfy one particular condition. That is, let me say if a cap is an operator, when it acts on a function, sum of two functions, when this operator acts on sum of two functions, then the result what you will get, that should be exactly equals to the result what you will get when you add the results of the two functions separately. So that, let me say, we're considering one simple illustration. So let us say the function f of x plus g of x. So on this, the operator is acting as a whole. So a cap of f of x plus g of x. And the result of this should be exactly equals to operation of a cap on f of x plus operation of a cap on g of x. So when this operator a cap is satisfying this particular condition, then that operator will be called as linear operator. So let us do one simple illustration. Let me consider an operator d by dx. And let us perform operation of d by dx on a function a into x power m plus b into x power m. And obviously, the result will be exactly equals to d by dx of a into x power m plus d by dx of b into x power m. Right? So here d by dx will be considered as a linear operator. So if you consider one more operator, say this one, square root. So if you perform square root of f of x plus g of x, that can never be equals to square root of f of x plus square root of g of x. Right? So that square root cannot be a linear operator. So that is the condition for linear operator, means the result of operation of an operator on sum of a function should be equals to results of the operator on the functions separately. That is about linear operator. So, and that's about the operators in quantum mechanics. If you like the video and if you feel the video is information for you, please like it, share it and comment in the comment section. And please do subscribe my channel and press the bell icon to get the notifications. Thank you.